Hello. Is this working? Hello.
Next speaker is Sanghamitra Dutta.
Hi, thank you everyone for having me here today. So today I'm going to talk about some strategies for fair and reliable machine learning that are deep-rooted in causality and information theory. In particular, an emerging body of work in information theory that is called partial information decomposition. So machine learning is entering into every aspect of our lives these days, such as hiring, education, lending, etc. So while these models are really great at learning all kinds of patterns present in the data, but blindly learning all these patterns can sometimes lead to unintended consequences, like propagating biases and disparities with respect to gender, race, age, nationality, etc., that can have adverse effects on people's lives, and in many cases is also disallowed by law. So when it comes to identifying, addressing legal disputes, or even informing policies and interventions, only identifying the final bias in a model is not always sufficient. We really need to dig deeper and understand how that disparity arose and answer another question that bridges the fields of fairness, explainability, and law. That is, how can we identify and explain the sources of disparity in machine learning models? So as an example, let us consider the hiring of a software engineer for a safety critical application. We have some inputs that go into a model and the model decides whether to hire or not. Now, it has been shown that even if these protected attributes like gender, race, age, etc. are not explicitly used as input to the model, the outputs can still be correlated with these protected attributes because the other features might be strongly correlated with these protected attributes. So, and this also closely connects with the idea of disparate impact. But then sometimes certain features are very important for a particular application. Like coding test score might be really critical in the hiring of software engineers. And there are also similar discussions in law which says that disparate impact may be exempt if it can be justified by some occupational necessity. Like coding test score may be critical for the hiring of software engineers, or weightlifting ability might be critical in the hiring of firefighters. But then aptitude test may not be so critical, as in this landmark court case of Griggs versus Duke Power. So the question that I'm interested in is, given a choice of critical features, how do we quantify if the disparity is exempt or non-exempt? And towards answering this question, our main contribution is a systematic measure of non-exempt disparity, which is the bias that is not justified by the critical features. So this is my problem statement or notations that I'm going to talk about right now. Z is the protected attribute which denotes gender, race, etc. Then we will have some features that go into a model and produce the model output y hat. Now the critical features will be denoted by xc, and all the remaining features which are non-critical or general are denoted by xg. And we assume that all of these features are generated from an underlying structural causal model or data generation process, which involves all of these latent random variables. Now the question is, given a choice of critical features xc, what is a good measure of non-exempt disparity? Once we have such a measure, it can be used either for auditing, that is to compute and see whether a model is showing non-exempt disparity or not. Or it could also be used during training, for instance, as a regularizer with the loss function. But before we get there, the first question is, how do we quantify this quantity? So one candidate measure is conditional mutual information or conditional independence. That is, the model will be fair if the output y hat is entirely independent of the protected attribute z, conditioned on the critical feature x. But in this work, we also make a key observation that conditional dependence can sometimes falsely detect bias or misleading dependencies, even when a model is causally fair. So to understand what I mean by this, I'll show a counterexample. So let's consider a causally fair model. Here we have the critical feature coding test score, which depends on gender or race and the true inner ability. Then we have the aptitude test score, which happens to only depend on the true inner ability. And then the model makes its decisions only based on this true inner ability U, which is independent of gender or race. So such a model is causally fair from the definitions of causal fairness. That is, the output y hat should not depend or vary with z when you fix all the inner abilities u. But if we naively condition on a critical feature here, we will falsely get a dependency because the conditional dependence is greater than 0 here. So one desirable property for such a measure of non-exempt disparity is that the measure should be 0 when the model is causally fair. So in summary, conditional mutual information or conditional dependence does not satisfy the causal fairness property. And this limitation actually leads us to look into this emerging body of work in information theory, which is called partial information decomposition, which further decomposes conditional mutual information into two quantities: unique information and synergistic information. And this unique information happens to satisfy our causal fairness property and some others. So what is this unique information? To understand this, we'll look at an example. So we consider two very similar looking scenarios. In one case, on the left, the critical feature xc depends on z, but the output doesn't depend on z, which is the gender or race. Whereas on the example on the right, the output has some information about gender z that is not in the critical feature xc, which is not fair. So conditional mutual information happens to be same for both of these examples. But a desirable property is to be able to distinguish between these two cases and say that in the first case, there is no disparity, whereas in the second case, there is. So unique information is defined as follows. It is the minimum conditional mutual information when the marginals between zy hat and zxc are preserved, but the joint distribution of the three variables are allowed to vary. So if you're familiar with Simpson's paradox or even interested in mutual information, unique information is essentially the intersectional dependence between mutual information, which is just dependence, and conditional mutual information. And this unique information will go to 0 whenever either of them goes to 0. And this quantity satisfies our property 1 as well as some other desirable properties. But then we look into some more nuanced examples, which are again non-faithful causal models, where even unique information alone might not be sufficient. For instance, these kinds of scenarios of mass discrimination, where the output might be like an XOR of gender and inner ability. That is, the candidates with men with high inner ability and women with low inner ability are being shown an ad, whereas the other two groups of people are not being shown an ad. So this remaining part, I might go a little bit quickly, but because of this limitation of unique information, we finally arrive at a causal measure that synthesizes both partial information decomposition and causality. And this measure satisfies some of the properties that I already discussed, as well as some natural monotonicity properties as well. But this measure depends on the true structural causal model or knowledge of the true structural causal model. But the idea is that I believe that even if this measure depends on the causal model, there is value in first finding a measure that satisfies all the axioms, however difficult it might be to compute, because then it can serve as a benchmark for other observational relaxations and help us understand their pros and cons. And also this observational unique information is actually good enough for a lot of situations, and only for the case of the mass discrimination is where we need to move on from the observational unique information to this measure that leverages both unique information and causality. Then we also have some impossibility results that no purely observational measure can satisfy all the desirable properties. But nonetheless, with partial knowledge or assumptions about the causal relationships, they can correctly quantify non-exempt disparity. And then we perform some case studies using these observational measures on artificial and real data, as well as some analysis on the CMU graduate admissions datasets. Now I'll very briefly touch upon two other problems that I'm also interested in. So one of them is this question of understanding social media and filter bubbles. Like, let's say a person gets to see ads that they really like. If you like to read New York Times, you only get recommendations from New York Times. If you like to read Fox News, you only get recommendations from Fox News. So how do we diversify recommendations in a manner that a person's interests are also retained? And here these kinds of exempt and non-exempt topic bias can play a role in understanding how should you diversify recommendations. Another question that I'm also very interested in is the quantification of fairness and accuracy trade-offs. So in this work, I use an existing measure of fairness, that is equalized odds, and I quantify the trade-off between accuracy and fairness using these tools called Chernoff information. So in summary, this work, my work bridges between several fields like causality and information theory to arrive at measures of fairness. And in future work, I'm also interested in understanding how these techniques can be applied, how can we arrive at better estimators for these quantities, as well as have broader conversations like what is the right interpretation of laws for algorithmic hiring, for which I also believe it is essential to collaborate with lawyers and social scientists. So thank you so much for having me here, and